When thinking of ChatGPT or Claude, we imagine a single massive brain answering our questions. But under the hood, modern AI deployments rely on a whole family of models, built in different sizes, working together to balance speed and cost. The ideal setup works like a triage system. If you ask a simple question, the system routes it to a cheap, lightweight model. But if you ask it to write complex code, it routes that prompt to a massive, highly capable model. This gets tricky when a conversation escalates. You might start with a basic request handled by a small model, but then ask a complicated follow-up. At that exact moment, the system needs to hand the conversation off to a heavier model. Here, we hit a massive computational wall, the switching tax. During handoff, the larger model has zero memory. It executes a prefill, forced to recalculate every word from scratch. This drains power, spikes server costs, and introduces brutal latency delays. True efficiency in AI routing remains out of reach until developers solve this exact bottleneck. We need a way to take a small model's active working memory, known as the KV cache, and instantly transplant it directly into the larger model. Researchers recently found a way to do exactly that by looking at matched model pairs within the same family, like the 14 billion and 32 billion parameter versions of Qwen 3. Despite size differences, their architectural DNA and memory structures, specifically KV head counts and dimensions, are identical. Therefore, data passing through the small model's lower layers predicts the larger model's higher layers, explaining up to 79% of variance in memory keys. If we can accurately predict those internal data patterns, we don't have to force the big model to slowly read the prompt. We can just use math to map the small model's completed homework straight into the big model's brain. The shared anatomy of these families creates a mathematical bridge. Developers can use it to skip the compute-intensive prefill phase entirely. To actually execute this transfer, the researchers built a specific tool, a 3-step closed-form linear mapper. Step 1 is extraction. The mapper selects the small model layers holding the most predictive value, pulling their data into a single concentrated block. Step 2 is filtration. Positional data, rotary position embedding, is stripped away, leaving only pure, unordered core data. Removing that positional awareness is a crucial innovation. It ensures the mathematical fit relies only on the content, making the transfer position-free. Whether your conversation is 10 words long or 10,000, the same exact mapping works. Finally, step 3 is translation. The mapper uses a statistical technique called ridge regression to instantly reshape the small model's data so it perfectly fits the large model's architecture. And locking in this formula only requires a tiny calibration set of 500 text sequences. Running this localized statistical equation takes a tiny fraction of the energy required to brute force recalculate thousands of text tokens from scratch. Through extraction, filtration, and translation, this mapper seamlessly converts the smaller AI's working memory into the exact native format required by the larger AI, enabling an instant takeover. Compared to standard re-prefilling, cross-model memory transfer is 2.7 to 25 times faster. The linear mapper retains between 73% and 98% of the large model's standalone accuracy, all without the large model ever actually reading the original prompt. For the few model pairings where that linear mapping drops in quality, engineers can deploy a slightly heavier nonlinear system, an MLP, to easily recover the lost accuracy. This transforms isolated monolithic brains into a dynamic, high-speed relay team that hands off work without dropping the baton. Eliminating the prefill bottleneck moves us toward liquid AI, an ecosystem where complex tasks cascade across specialized models without the redundant compute and latency that previously made routing too expensive to use.